Buckies and Buckets. Today I will be demonstrating you a circuit, and now we will be performing some math involved and explaining you what's going on in this whole circuit. In front of you is basically a parallel circuit, but within the parallel circuit we have a series circuit involved. Now the current, which is from your EMF, the battery, flows into the first setup junction point. From there, the current splits off to I1 and I2. The first current goes through here, second current comes back through here, and they both merge at this second junction point. From there, it goes to the switch, and the current flows back to 0 at the end. Pause. Now let's do some math. What we do know is there is resistance in this circuit itself. What we don't know is the current and the resistance of the loop itself. So let's do some math. What we're trying to find is the current flowing through the circuit and the resistance on the wire itself. Now, here's what's given. We do know that each light bulb produces 0.5 watts of energy, and there's 5 light bulbs in the circuit itself. So 0.5 times it by 5 gives us 2.5 watts. Okay, so now we need to know how much voltage we have. Now this battery, as we can tell, is a 9-volt battery, but in fact it is not a 9-volt battery. As I demonstrate here, this battery only contains about, let's round up to 8, give or take a few. So our voltage now is equal to 8 even. So, given that, what do we do now? According to Ohm's law, P, which is power, equal to the current times the voltage. Power is 2.5 watt. Voltage is 8 volt. So, 2.5 watts equal to 8 voltage times the current. Doing the math, we have 0.3125 amps involved in this circuit. So we also do know that V equals I/R, which is current times resistance. We found a current, which is 0.3125 amps. A voltage stays the same, which is 8 volt. Now that equals to 0.3125 times resistance. Doing the math again, 8 divided by 0.3125. Your resistance equals to 25.6 ohms. So what basically tells us that the resistance in the copper wire itself is 25.6 ohms, and the current at the beginning is 0.3125 amps, and at the end it goes back down to 0. Okay.
Here we have is a parallel circuit. It consists of basically 2 series circuits strung together in a parallel fashion. Whereas if one were to go off, the other would have stayed on. Now what happened if I were to break one light bulb on the first series circuit? Of course, as you know, the second series still remains on because only the first circuit is broken off.
Here we have basically the same circuit, but what's different is that this light bulb is out. Now, does that mean it changes the identity of the circuit? No, not really. This is still considered as a series, but connected like this is still considered as a parallel. What it is that in the 18th century, a guy made a discovery. What he did was this. Before, usually it was just a filament inside with two conducting wires that lights up the filament. But what he did was he added an extra strand to it. If you actually look closely, there's a little strand connecting the two filaments together. But that right there, that's what's called the internal shunt. When that shunt, as long as it's not broken, the rest of the light was still lit. Whereas that bulb will be the only one who burns out.